Okay, so now we're going to talk about molecular polarity. So again, at this point, you should be able to figure out what kind of bond something has. Non-polar covalent, polar covalent, or ionic. Based on electronegativities, if I give you the numbers, all you do is subtract. You should be able to draw the Lewis structure. So you absolutely have to be able to do that because this stuff depends on your ability to draw Lewis structures. And the 3D VSEPR shape of things also makes a difference. Not as much as you might think, but it does make a difference. So we're going to talk about something called dipole moment. And what is dipole moment? Well, that's when you have molecules that have a polar covalent bond. One end of it is a positive end, and one of the molecules a negative end. It's called a dipole. So if you remember when we were talking before about the bond types, and I would draw in the little delta positive, delta negative, that if you have a molecule like that, that's a dipole. It's got one end that's partially positive, one end that's partially negative. Okay, so dipole moment, how do you know if something has it? Well, first of all, it has to have a polar covalent bond. That means 0.3-ish up to about 1.6 electronegativity difference. When you subtract the numbers, you get a number between 0.3 and about 1.6. So if it's ionic, it doesn't count. If it's nonpolar covalent, it doesn't count. Okay. And in that situation, you have one atom that has a stronger pull. Remember, it's a tug of war for the electrons in the bond, and the electrons will spend more time near that atom, and that creates a bond dipole. Not the molecule, not a molecular dipole, but a bond dipole. So you have H and Cl. Okay, Cl is much stronger. It pulls the electrons to itself, negative, positive, meaning in the electrons, they're being pulled this way. That glue is being pulled that way. That's what a bond dipole is. Then you need to have, in order for it to turn into a molecular dipole, which I realize is confusing, the molecule has to be asymmetrical so that those bond dipoles don't cancel out. So it has to be oddly shaped. Okay, either the outside atoms are different elements, because that creates a different strength of bond polarity, or there are lone pairs of electrons on the central atom. Either one of those situations will result in a dipole moment on a molecule. So here's CH4. Perfectly symmetrical all the way around, no dots. It has a polar covalent bond, though. If you subtract those numbers, I don't know, what is it, 0.8, I think, something like that. It is a polar covalent bond. The electrons are being pulled in towards that carbon, but because it's perfectly symmetrical in the shape, it is a non-polar, has a polar covalent bond, but it is a non-polar molecule. Or you could say it has no dipole moment. You could say one of the two things, either one. Because all those electrons are being pulled in from opposite directions, they all cancel each other out. And so therefore it is a nonpolar molecule, even though it has a polar covalent bond. Okay. SO2 in water, though, on the other hand, what happens is oxygen is more electronegative. It's pulling the electrons this way. And what happens is there's nothing up here to help compensate. And so as a result, because of that lone pair, this one has a polar covalent bond, because if you subtract the numbers, whatever it is, and it is a polar molecule. It has a dipole, meaning down here it gets pulled negative, up here it gets pulled positive, because there's nothing to compensate on the other end. So the bond dipoles created between the atoms do not cancel out due to the presence of lone pairs. Same thing for water. Water, the electrons are being pulled inwards to the oxygen, but there's again nothing up here to help compensate, so it gets the negative end, this gets the positive end. It has a dipole moment. They are polar molecules. It's important to distinguish because the word polar is used a lot. And what happens in something that is linear, because the electrons spend more time here, that gets a partial negative. Because the electrons spend more time here, it gets the partial negative, and this end gets the partial positive. So polar covalent molecules, like the ones shown below, have a positive end and a negative end, like a magnet. That's why it's called a dipole. It's got two of them. One pole is one way, one pole is the other way. And they are based on electronegativities and shapes. So the electronegativity is how the electrons are shared. But if you had something like carbon dioxide, the electrons are being pulled this way and being pulled that way. They cancel out because of the symmetry. And this is a non-polar molecule. Even though the bonds are polar and the electrons are being pulled here and here, because of the symmetry of the molecule, they cancel out and it doesn't have a dipole moment. So that is not a polar molecule. This is a polar molecule because of the ends being pulled and because of the shape. If you have something like water, this is water, remember it's got those two lone pairs, the electrons are being pulled inwards, and what you get is you actually get a center of positive charge kind of in the middle. The electrons are getting pulled that way, and the positive charge is the other way. But you definitely get a dipole moment. So, false Lewis structures are drawn. I'll draw them on here for you. Determine if the molecule has a dipole moment and explain your answer. So, the Lewis structures. Oh, heavens, I'm not going to have much room. All right. Let's go back. So, the bond type. Polar covalent, polar covalent, polar covalent, polar covalent, polar covalent. This one's non-polar covalent, and this one's polar covalent. So they're almost always polar covalent. So this one's not because it's all the same atom. So if it's got, it has to have, first of all, it has to have a polar covalent bond to turn into a polar molecule or have a dipole moment. Since this one is non-polar covalent, the answer is no. Okay, it's got to have that bond type. So I'm going to draw the Lewis structures best I can. So CO2 looks like this. And because of its perfect symmetry, it does not have a molecular dipole. H2S has got lone pairs on the center atom. Because it has those lone pairs, it's a bent shape, which means it's not symmetrical. And so therefore you would say, yes, it has a molecular polarity. HCN looks like this. And again, it's not symmetrical. Therefore you would say, yes. Okay, CCl3H looks like this. And again, you're dealing with something that is not perfectly symmetrical. And so, yes, it has a molecular dipole. All right, NH3 looks like this. It's got the lone pairs. So even though the atoms around it are all the same, it has a set of lone pairs on the central atom. So yes, it has a molecular dipole. And then CCl4 looks like this. And since it's perfectly symmetrical and there's no dots on the central atom, you would say no. So what you're looking for is, first of all, polar covalent bond. Okay, it has to have that first. And then either dots on the center atom or different atoms around the center. And then you would write yes. Okay, intermolecular forces are next, and this is kind of where we've been building up to. Okay, I'll talk about that in the next movie.